Hey everyone, how's it going? Welcome to today's A-level physics Sunday session. How are we all doing? Are we pumped? Hey Ryan, any tips for AS level physics students? So I guess you only just started a month or so ago then. Yeah, okay. Um, any tips? I can give you a couple of, hey Jonathan, how's it going? I can give you a couple of really blanket ones that you've probably heard in other places, like I guess not worrying too much about memory for now, focusing more on understanding now, and then uh, more about remembering all the details when you get closer to the exams. Don't be too intimidated by your first AS mock. I remember my first AS level physics mock, I completely crash and burned. Uh, just because I wasn't ready for the phrasing of questions and stuff compared to GCSE. But you get used to it pretty quick. What's my special interest area of physics? Yeah, so I work on something in between putting together quantum theory and general relativity. So quantum gravity is the tagline. And a bit on what's called quantum computing, which is essentially using the laws of quantum physics to make computers better, more efficient. So that's my area. Okay, let's see how we're doing. Okay, so I think now is a good time to get started. So hopefully you can all see my notes. A-level physics, stationary waves, and you might just about be able to see this in any old guitar. It's a particularly happy one. Okay, so what are we up to today? Well, we're Snap Revise, and just a bit more detail on that. So about me, my name is Matt. I'm the head of physics here at Snap Revise. I'm currently doing a physics PhD at Oxford. And as I was just saying a second ago, it's all about using quantum theory to make computers better. And yeah, I've been tutoring physics for at least 4 years now, in fact, maybe more now. Okay, so thing number one, Snap Revise is a lot more than what you just see on YouTube. So we like to do various things on YouTube, but there's a lot more that you can see on the Snap Revise website itself. And right now, if you want to take a look, now is a particularly good time because using this code here, you can get 25% off all courses. And I'll talk a bit more about what the courses are and how it's different to what we're doing on YouTube at the end. So for now, let's talk about stationary waves. Now, I don't know if you guys will have seen stationary waves before. I mean, it's typically an AS topic, but of course, people doing AS, you're only about a month in. So there's a high chance you won't have seen this. So feel free to ask as many questions as you like. It doesn't matter how stupid you feel like they are. They're always good questions. The more questions you ask, the more I know about how you're getting on and how what I'm saying is coming across. So yeah, as all action in the chat is encouraged, just go for it. So the objectives today are to understand the concepts of phase and superposition. Phase is just a way of measuring how far through the cycle of a wave you are, but we'll put some maths on top of those words. We'll describe how stationary waves are formed. They're kind of a very strange type of wave. And we'll do some bits and bobs of maths on top of the idea of a stationary wave. All right, okay. So before we get into the main topic, we usually like to do a quick overview to get us up to speed on the things that we need for today. Today's about stationary waves. Stationary just means staying still, so we know what stationary is. So what we need to know about is waves. So I've got a picture of some kind of a wave here. Maybe these are the particles that make up a string or something, and someone's wiggled the string, and then I've taken a photograph. I've got some kind of a wave like this. Okay. There's a few things I want to know about this wave. A few words that are going to be useful. Does anyone know the word for this height here that I've drawn? What exam board is this likely to appear in? It's likely to appear in all three. Just after this intro slide, we will actually do, we'll actually mention how it looks for each of the three exam boards. Okay, you're absolutely right. This is amplitude. I've seen there's something about lagging in the chat. Let me know if more people are having a problem with the lag, and in particular, if you can't figure out what I'm saying. Good, yeah, so this is amplitude. Good. Okay. What else do I want to know? So more general, actually, amplitude is just like the maximum possible displacement. I'm also going to be slightly more careful. I think I really want to go from here, because this position here, what's this called? It's like the position that a wave is oscillating around. We have a special name for that. So the peak is the place where the displacement is a maximum. So this will be the peak up here, but that's good. We definitely wanted that down as well. Medium, yeah, it's essentially a fancy physics word for medium. It's good to get used to this word because it will come up a lot. We call this the equilibrium position. And for now, you can just see that as fancy middle. Absolutely right. Good. Okay. Okay. One of the key lengths that I'm interested in is this one that I've drawn at the top here. What's that one? So it's the distance from one peak to another, if you like. Not quite the period, although we will come back to the period. This is the wavelength, absolutely right. It is the distance between one peak of the wave and the next. It really is kind of the length of one cycle of the wave. And yes, we'll give it the symbol lambda usually, and it is the wave length. Good, okay. You mentioned the period. Can anyone tell me what the period is for a wave and how it relates to frequency? So it relates to frequency by some kind of a formula. And I should mention, I'll mention what frequency is over here, but if someone can tell me what period is, that would be great. So frequency, F, is number of oscillations per second. Good, you're absolutely right. Frequency is 1 over period, or period is 1 over frequency. What is the period? So the period here, which we give the symbol T, is the time taken for one oscillation. For one oscillation, one cycle, if you like, of the wave. Okay, so that's all the wave stuff that we're going to need to know, except for one other key point, which is why waves are interesting. So the crazy thing about waves is they allow you to transfer energy without transferring matter. So let's see what this means. Usually, let's say there's a bottle on the other side of my room, and I want to try and get it to fall over. There's some delay. Okay, do let me know if you can't hear what I'm saying, and I will repeat anything that you guys haven't caught. So apologies for that. So let's say there's some kind of object that I want to knock over. Then one choice would be to throw a ball at it. Essentially, what I'm doing is transferring energy to the bottle. And the way I'm doing that is by transferring it to the ball carries the energy. So it's a piece of matter that carries the energy over to the bottle and then knocks it over. Now, waves are very different because I can do something like try and knock a bottle over by sending a wave towards it without ever actually having to send any matter, like the ball, for example. So that's also why waves can be quite useful, or one of the reasons. So I know people were asking about the spec points, not the spec points, sorry, the exam boards. So here's the spec points we're covering for AQA. Okay. Here's the ones for OCR. And here are the ones for EdXL. So all of this stuff is relevant for all 3 exam boards. Okay, so let's get going with the main session. So we're going to start off by talking about phase and phase difference. Now, phase is just a fancy way of talking about how far through a cycle we are. So let's say this is, and we typically take this point here to be the start of our wave. And let's say we take this point here to be the end of our wave. We want some kind of a scale for measuring how far through our cycle we are. Now, if this is a wave going through space, maybe you could use just distance. I'm 4 meters through my oscillation, 6 meters. In more general, we want just some unit that represents how far through an oscillation we are. And okay, this quantity, we're going to call it phase. So the phase of a point on a wave describes where, or maybe how far through an oscillation that point is. So the phase tells us how far through the cycle we are. And then the phase difference, well, that'll be the difference between how far through each point is in an oscillation. Now, phase difference, it's actually hard to say in words. This sentence might be a bit confusing, but it'll be much easier just to give one example in maths. So I'll do that in a second. Okay, so now we're going to pick some units for phase. Essentially, we need to say what the start is and what the end is. So we're going to always say that the start is a phase of 0. And then what we can do is we can either split up the distance between the start and the end into degrees. If we, so that's just one unit we could choose. So we could say the end is 360. And then we could say, okay, we can just talk about how many bits of 360 we are through. One other option, so this is called using degrees. We could also use what are called radians, which will come up again when you study circular motion. Okay, so path difference is specifically the difference between how far through each wave is its cycle in meters. So the point is that phase difference, we're just using some kind of abstract number like we use, okay, so 360 degrees is the end, then what would be 1/4 of the way through our oscillation? All the way through is 360. So what we need is just 1/4 of 360. So that'll be 90. Yeah, absolutely right. Really nice. Good. Okay, 90 degrees. So we could call that 90 degrees. Or if we were calling the end 2 pi, that would mean we were doing things in radians. Then we could say that this point here is equivalently pi over 2, because that is 1/4 of 2 pi. Okay, good. Now, if 2 points are at the same point in their oscillation, then their phase difference will be some number multiplied by 2 pi, or equivalently, some number multiplied by 360 degrees. So here's the idea. The end here is 360 degrees away, or we could go for the next end, which is going to be another 360 degrees away. So then the phase difference between this start point and this ending point, another point that's in the same point in its cycle, is going to be 2 lots of 360. It could have been 3 lots, 4 lots, 5 lots, etc. In general, if you're at the same point, if you have 2 points which are at the same point in their cycle, but maybe many cycles on, there'll be some number of 360 degrees apart. Good. Okay. So that's phase. Now let's talk about superposition. So phase is all about describing a particular wave. Phase difference can be for 2 waves. Superposition is about how 2 waves interact. So when 2 waves meet, the resultant displacement is given by the sum of each wave's displacements. So let's look at an example. Let's say we have a wave here with a displacement x1, which is just moving along the right-hand side. So eventually it's going to reach the middle here. And then we have another wave with displacement x2. And this is moving along in the other direction. Okay, so eventually that's going to reach here as well. What will be the displacement when these 2 waves meet at this point here? So I might not be able to go through the whole phase difference bit. If you have something specific, then I can answer something kind of a bit more specific. I'll also just mention an example. So let me do an example of phase difference. Let's say I've got a point here, which is at phase 90. I've got a point here, which is 3/4 of the way through an oscillation. So this is at phase 270. So point 1, point 2. The phase difference is given by the difference in their phases. So here it would literally be 270 minus 90, and that would be 180, which actually kind of means they're half a cycle apart. So that's what the phase difference is. You take the phase of one point and you take away the phase of another point. Okay. So how did I get 270? Yeah, well, this point here was 3/4 of a way through a cycle, and a whole cycle was 360. So I took 3/4 of 360. But I wouldn't worry too much about that bit for now. Okay, so when these 2 waves meet in the middle, they're going to make one bigger wave, and the wave's displacement is going to be given by adding this displacement to this one. So we're going to have x1 plus x2 here. Okay, no worries. Okay, so let's take a look at another. Let's say now I have a wave going along like this, displacement x1. And let's say I have a wave going along in the opposite direction. And let's say it has a displacement x2. And let's say it's a bit smaller than x1. So all in all, when these waves meet in the middle, we've got a wave here and a slightly smaller wave here. I didn't draw that so well. Let's say like this. x1, x2. This time, when we add these amplitudes together, because they're in opposite, because the waves are going in opposite directions, they work against each other. So in this case, we'll have a displacement, we'll have a new wave, a small one, whose displacement is given by x1 minus x2. Okay, so we have special words for these. These are often called interferences between waves. So we have a word for the type of interference we have at the top here, and a word for the type of interference we have at the bottom. I won't write it for now, but feel free to say what it is in the chat and then I'll fill it in. So for now, while you're doing that, I'll just fill in some notes over here. So when two peaks or troughs meet, the resultant is the sum of amplitudes. That's what we had over here. And then when a peak meets a trough, the resultant is the difference between the amplitudes. Nice, absolutely right. Yeah, good. So this is called constructive interference. And this is called destructive interference. All right, perfect. Well done. That looks really great. So, last part before we have a go at a couple of questions. We're going to now talk about the big topic for today, stationary waves. So, we're not going to worry in too much detail what continuous and coherent mean for now. But when two continuous coherent waves meet, something quite surprising happens. So continuous and coherent here means, well, continuous just means it's a wave. And coherent means they have something like the same phase difference or a constant phase difference, which essentially means something like they have the same wavelength and the same frequency. So we have two waves that are essentially identical, but maybe they're moving in opposite directions. Same wavelength, same frequency. Then some pretty weird stuff happens. So let's say the pink wave here is moving to the right. And let's say the orange wave here is moving to the left. Okay. So there are going to be some points here which work together and some points which work against each other. So let me just write here. There will be some points on the waves which are constantly, and we'll talk about this constantly bit in a second, so don't worry if it doesn't make too much sense for now, in/out of phase. So we'll come to this in a second, but I'm going to put in an extra point now, which I think will be easier to interpret this in terms of. So as a result, there will be points of constant constructive / destructive interference. So this second bullet point seems like a super wild claim. There are going to be some points along this line here where the waves are always working together and some points where they're always working against each other. That's the claim of this second bullet point. And now let's take a look. Okay, so let's look at a point where they seem to be working together. Well, how about this point here? Here, both waves are trying to pull upwards. So here, if we were to add them together, they'd make an even bigger wave. That's constructive interference. Okay. Now let's see what happens as time goes on. Well, as time goes on, the pink wave is going to move to the right, as we drew here. So, okay, the pink wave here is going to move to the right a bit. And the orange wave, we said was going to move to the left. Okay, so here's the orange wave, and the orange bit's going to move to the left. So what you might see happens is that this point of the orange wave is going to end up here. And this point of the pink wave is going to shift in the opposite direction to here. So again, we're going to have 2 points on the wave. They're both a bit lower down now, but they're both working together. They're both pointing upwards and by the same amount. So even though I let time run a bit and I let the waves move, they're still working together. They're still doing constructive interference. Okay, now there are some points along this line where things get pretty wild. So a good point to look at would be something like this one here. And let me get this more close. This one here, this one here. Yeah. So let's look at these 2 points here. So these 2 points are currently working against each other. They are completely out of phase. And one way of talking about it is, well, one's pulling up, one's pointing down. So this is destructive interference. Okay. Now, as we let time run on, the pink wave moves to the right a bit. So this peak that was here is going to end up over here. And this peak of the orange wave, well, the orange wave is moving the opposite direction. So that's going to move over here. So at a later time, we're going to have the 2 peaks and it's still going to be working against each other. So when you have 2 waves going in opposite direction, there are some points where they always work together and some points where they always cancel each other out. So as a result, there are going to be some fixed points in the resultant wave, the superposed wave, that are never moving. So this point here, there's going to be another one here where the waves are working against each other. Waves are working against each other here as well, and here. All these points, there's going to be no displacement at all. In the rest, the resultant wave, well, it can't move left or right, the wave that we get in the end, because these points are fixed. They're always going to stay still. So instead, the resultant wave appears to stay still. Okay, so what we actually get is a wave, and you may have seen this picture before, that looks like this. So at one time, it's going to look as I drew here, and at some time later, everything's going to flip over and it's going to look like this. So it looks a lot like a normal wave, except it doesn't move left or right. It just goes up and down, up and down. This is what we call a stationary wave. Okay, good. So does anybody have any questions? How are we feeling? We'll have, if you're worried, we have a couple of exam questions that we're going to look at, which might also help. Okay, let's have a go at some exam questions. Just let me know if you have any other questions. All right, nice. Okay, cool. Right, okay, let's have a go at a question. Figure 4 represents a stationary wave formed on a steel string fixed at P and Q, which has been plucked, or when it has been plucked, at its center. Okay, 5A. Explain why a stationary wave is formed on the spring. Now, we did a lot of work to understand exactly why we get this wave that can't move left or right. But actually, what we have to say in the end, the stock answer, isn't as complicated. So this is something you almost want to end up having learned by rote in the end. So, okay, the first thing we need to think about, though, is why plucking a string would create a stationary wave. Well, what do we need for a stationary wave? We need 2 waves moving in opposite directions. Why would we get that when we pluck the string? Well, if I pluck the string, maybe originally a wave goes off to the left, a wave goes off to the right, and then each one hits where the string is fixed on either end and gets reflected back. So now we've got one wave going one way, one going the other, moving past each other, and that's what we needed. So that's the key point here, really. Plucking string creates two waves moving away from center when each wave hits P or Q, they are reflected to make two coherent, which is just fancy language for same frequency, same wavelength, two coherent waves moving past each other. This creates points of constant constructive / destructive interference. And so a stationary wave. Depending on exam board, you might sometimes see a stationary wave called a standing wave as well. Okay, good. Let's have a go at another question. Whoops. When a note is played on a violin, the sound it produces consists of the fundamental and many overtones. Exactly what that means we'll see in the next part of the section of this session. Figure 8 shows the shape of a string for a stationary wave that corresponds to one of those overtones. Okay, the positions of maximum and zero displacement for one overtone are shown. Points A and B are fixed. Point X, Y, and Z are points on the string. Okay. 6AI. Describe the motion of point X. Okay, well, what can we say about point X? Point X is a point on the string, and we have to talk about what it's going to do. Well, it's on a stationary wave, and the point in a stationary wave is that all the points on the string just moving straight up, straight down, with some of the points never moving at all. So here, quite simply, this point X will constantly move up and down, cycling with a fixed, well, up and with a fixed period. I could have written this easier by just saying up and down periodically. Period. Okay. Okay, good. The recording of this will be on the channel afterwards, so you'll definitely be able to watch this back afterwards. Yeah. Okay. Now we're asked to state the phase relationship between some points on this standing wave. Now, this is interesting because this is actually a much more subtle question than it first sounds like. Okay, so they're asking something quite specific here. They're saying, okay, let's treat each of these points as doing its own oscillating thing backwards and forwards. And it has some kind of a cycle, right? I don't know what we want to call, maybe we could call when it hits the middle here, that can be point 0, that can be 0 phase. And then when it goes down, up and back round, that can be a phase of 360, etc. Okay. Now they ask us to state the phase relationship between a few of the points on these waves, and they're all doing their own oscillations. And we can talk about the difference between how far through their own cycles they are. Okay, so I need to introduce some terminology that I haven't mentioned yet. So when two points are at the same point of their cycle, we call them in phase. And when 2 points are 180 degrees apart in phase, we call them in anti-phase. So this is a 180-degree phase difference, and this is a 360 or a 0-degree phase difference. Okay, so it's just extra fancy words. So these are the kind of words that they're looking us to use when they ask us to state the phase relationship. So the phase relationship between X and Y. Well, X is at the top of its oscillation here. What they've drawn here is the maximum point, the maximum height that point X can get to. And Y is at the bottom point. So there are opposite sides of their oscillations. And so they're actually going to be 180 degrees apart, or more simply, they are going to be in what we call antiphase. Okay. Whereas X and Z are both at the top of their oscillation. Z is higher than X, but the point is they're both at the top of their oscillation. Therefore, X and Z are in phase. They're at the same point of their oscillation. That is the top bit. Okay, so now we're ready to talk about some properties of stationary waves. So this is slightly shorter than the previous part. One sec. Just a quick issue. Good. All right, so properties of stationary waves. We've defined what they are. Now we're going to look at them in more detail. So we're going to start by describing some points. The nodes are going to be these fixed points that don't oscillate. So a node is a point which always has no displacement. Okay, so where are the nodes on this diagram? Well, this is a diagram of a standing wave, and the points that aren't moving are this one, this one, this one, this one, this one. So these here are the nodes. Good. Okay, now let's think about the antinodes. So you might be able to predict that the antinodes are the opposite. So the antinodes are, an antinode is a point which is always at maximal displacement. So it's actually easier just to draw them than to say what they are. They're this point, or strictly, I guess I'd say this point, this point, this point, this point, etc. Now, it's not that they don't move. They're not stuck at maximum displacement in that they just stay there. It's just that they're always the most displaced bit of the wave. Everywhere else on the wave, no matter what point you're at, will be a bit less displaced than these antinodes. Okay, so let's say some more stuff. If the two waves originally had a wavelength lambda, then we can draw that wavelength on these diagrams. So the distance between any two nodes is actually half a wavelength. That's just one other thing that we should mention. Okay. So now we're going to talk about harmonics. So what we're going to be talking about here are all the different types of stationary waves that you can make when you fix a particular length of string. Okay, so a stationary wave can be formed on a string in the way that we saw before in the exam question. You pluck the string, it sends out two waves to the ends of the string where they're fixed, and then they get reflected back, move past each other, and make the stationary wave. So a stationary wave is formed on a string when a progressive wave, or two progressive waves, is reflected back on itself. So we're imagining when we pluck the string, we send out one wave that has many directions, gets reflected back on itself to make two waves. Good, okay. Now it turns out that you can only do this at certain frequencies of waves called harmonics. So I fix my length of string, and I want to find what stationary waves I can have. And the point is, the ends of my string are fixed, and as a result, they can never move. Therefore, you must have a node here and a node here. So what we need to know, and this is going to be the key thing really here, is let's say this is the length of my string, which I'm going to call L. Then how can I write the wavelength of my wave in terms of this length? So that's the key question. The wave has some wavelength lambda. And if we look back here, we can kind of see from a stationary wave diagram what this half loop of a stationary wave is. Yeah, half of a stationary wave, this thing here we said was half a wavelength. Good. So this here is half a wavelength. Therefore, the wavelength itself, where if half a wavelength is equal to L, the length of the string, then the wavelength is equal to 2 times the length of the string. Nice. Well done. Good. Okay, so we've got 2 nodes here. Now we can go a bit higher and think about what if we add one more node? So now we've got 3 nodes. Okay, good. Then what's this? Well, this is L, but it's also lambda. Here we have L equals lambda. Okay. Then we could go for 4 nodes. Okay. So for 4 nodes, let's see. Well, now we've got L again, but actually this time it's one whole wavelength and another half. So that's 3 halves of a wavelength. So these are the kinds of wavelengths that you can fit on the string. Okay. Now we have names for these special wavelengths or frequencies you can fit on the string. We said they were harmonics. We call this one with 2 nodes the first harmonic. We call this one the second harmonic, and this one the third harmonic. So note there's always one more node than there is the number in front of the word harmonic here. First harmonic has 2 nodes. Second harmonic has 3 nodes. Third harmonic has 4 nodes. Okay. Okay, so this is the last content slide. And then we just have a couple of exam questions to look at. So new concept, super important concept actually, for engineering and for music, and I'm sure, and actually for theoretical physics, for all sorts of things. The fundamental frequency of a string is the frequency of its first harmonic. So take your favorite string, find out the frequency of its first harmonic, and we call that the fundamental frequency of the string. Okay, good. Okay, going back, we have a formula for this thing. The formula for the fundamental frequency is it's given by 1 over 2L. Kind of makes sense. We had L's and 2L's hanging around before. And then 2 pretty crazy looking new things. A T, but not the period, something else, and a mu, which we'll have to introduce. So essentially, we've got this string. We want to know what frequencies were allowed on it. And this depends on the length of the string, but it also depends on a couple of other things. It depends essentially on the speed, and in particular, the speed depends on the mass per length of the string. So essentially how dense the string is, and it depends on the tension in the string. It kind of makes sense. You might know if you've ever done something like tune a guitar, as you increase the tension, you change the kind of frequencies that the string wants to let out. And that's exactly what's happening here. And similarly, you might choose different thicknesses of strings to make different sounds as well. And that's this bit at the bottom here. Okay, so other harmonic frequencies are going to be whole number multiples of F0. So for example, the second harmonic for each harmonic, all we have to do is take F0 and multiply it by this number here. So the frequency of the second harmonic is given by 2 lots. So frequency equals 2 lots of F0. Okay, so that's going to be 1 over L square root of T over mu. Good, okay. And actually, if I wanted to find the velocity of a wave on a string, and we could have done this for the first or the second harmonic, well, let's take the frequency, which is this, and multiply by the wavelength, which for the second harmonic was L. Okay, then we have L. Well, we have this bit. I write it like this. It's equal to F lambda, which is going to be equal to 1 over L T over mu times L. In other words, the square root of T over mu. So this bit here really is the velocity, if you like. Okay, so for the nth harmonic, we will take the frequency to be n times the fundamental frequency. And, okay, so that'll be n over 2L. There's an n, sorry, T over mu. And there's not too much else to say other than that actually, if we use this velocity here, then we can find wavelength in general is going to be given by, for the nth harmonic, well, it's given by velocity over frequency. This thing is some kind of a constant. It doesn't depend on what harmonic you're on. The speed is always the same along the wave, it turns out. This is just a kind of a fact that you'll need to remember. And this actually ends up giving you a formula. You don't need to remember this derivation, but it would be worth remembering this formula here. The wavelength of the nth harmonic is 2L over n. Okay, so there was a lot of information there. There's a lot to go through with stationary waves. How's everyone feeling? Do ask if you have any questions. And again, we will do some exam questions to try and help with any gaps. N is the number of the harmonic we're on. Okay. And then you're going to say, what's the number of the harmonic we're on? Well, we called the first wave we could have the first harmonic. The one with one more node, we call that the second harmonic. Next one will be the third. And in general, you could go on and on and on to get the nth harmonic. And it's that n. So the wavelength for the third harmonic is 3 lambda over 2. It's 2L over 3. So you can see it here, actually. Here, for the third harmonic, we have that lambda equals 2L over 3. And for the nth harmonic, we're going to have that lambda equals 2L over n. So it's just what you're seeing here, but taken on and on and on. Okay. Good. 2s and 1s. Nice. Okay. Let's have a go at some questions. Figure 4 shows a side view of a string on a guitar. The string cannot move at either of the two bridges when it is vibrating. Okay. When vibrates, so it's fixed here and here, which might sound familiar. When vibrating in its fundamental mode, the frequency of the sound produced is 108 hertz. Okay. Calculate the wavelength of the fundamental mode of vibration. So we have some more information in the diagram here as well. So fundamental mode, that was the first harmonic. So the first harmonic, how did it look? Well, it was the biggest wave I could fit on the string, and that looked like this. So if this length here, this L, is equal to 0.64, what's the wavelength equal to? What's the wavelength of this wave? We're kind of looking at part of the wave here, but not the whole thing. One way to think about it. It's like there's a whole extra part here, right? So this wavelength here is in fact 2 times the length of the string. and that's going to be 2 times 0.64, and that's going to be 1.28 meters. So now we're asked to calculate the speed. So what formula can I use to calculate the speed of a wave if I know the wavelength and I know the frequency? What can I use? It's a formula that I briefly mentioned in the last slide today, but you may not have seen before. So the formula was V equals F lambda. That is the velocity of a wave. Yeah, absolutely right. Nice. Yeah. The velocity of a wave is the frequency of the wave multiplied by the wavelength of the wave. Good. So here we have a frequency of 108 multiplied by a wavelength of 1.28. We can chuck that into a calculator and we'll get 138.24 meters per second. Good. Okay. And you probably want to round that in the exam. But for time's sake, let's go to the last question. Okay. While tuning a guitar, the guitarist produces an overtone that has a node 0.16 meters from bridge A. Okay, there's a node here. So what were the nodes? The nodes of a stationary wave, they were the bits that don't move. So we know there's a point that doesn't move here. Okay, on figure 5, sketch the stationary wave. This should really be a stationary wave. There's a lot of answers to this. Sketch the stationary wave produced and label all nodes that are present. Okay, so let's take a look. Well, we know we're fixed here, here, here. Everywhere I've drawn an X, we must be fixed. And we got to try and fit a wave. Well, the key here is that the gap between any two nodes is always the same. So we can draw another one, which is going to be another 0.16 meters. That'll take us to 0.32. We can draw another, that'll take us to 0.32. Let's get that right, sorry. So 0.32, good. Then we add another 16 to get 0.48, good, and then 0.64 at the end. Okay, so this is going to be the setup, and we just have to fit a wave on top of it now. So we can draw this, and then we'll draw the other bit of the stationary wave as well. So this is just a classic way of drawing a stationary wave. Okay, for BI, calculate the frequency, and label all the nodes that are present. Yeah, we've done that, okay. Nodes, here, 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 and here. Good. Calculate the frequency of this overtone. Okay, interesting. So there's a few ways of doing this, but there's one really simple way of doing this, which is by going back to here. We said the frequency of the nth harmonic is n times the frequency of the fundamental harmonic. Now, we already calculated the frequency of the fundamental harmonic. We did it, well, we were told it, fundamental mode 108. So for the nth harmonic, we would have n times 108, the fundamental, and we just need to know what harmonic we're on. Well, for each harmonic, we always had one more than that nodes. Here there's 5 nodes, so we're in the 4th harmonic. And so the fundamental frequency, the frequency of the 4th harmonic is 4 times 108, which is simply 432 hertz. Okay, so a couple of things to mention. First of all, what you should now be able to do, or what you've now had a taste of, you should now be able to understand these concepts of phase and superposition. Should be able to describe a bit about how stationary waves are formed and define nodes and harmonics of stationary waves, and use, or at least get used to using a couple of these formulas. Okay, so it's really worth practicing working with these. Just a couple of other things to mention. In the meantime, let me know if you have any questions while I'm saying this stuff, and I'm happy to try and answer them as well. So thanks very much, everyone who's come. And thanks for all the engagement in the chat. Just so you know, there's more web classes coming up on YouTube. So we've got a biology one coming up for A-level. We've got another physics one coming up. So there's all sorts of stuff coming up there. And also there's this 25% off code that I want to tell you a bit about now as well. And in fact, we'll just go for a quick stationary waves quiz to round things off. So let me just get a stationary waves quiz up. 1 second. Here we go. So right now, you should all be able to see my screen. And luckily for you, that means that you're now looking at the Snap Revise website. Now, there's all sorts of stuff I could tell you about here, so I'll just tell you a bit about it. Doesn't matter too much about the kilohertz. I should have spotted that, but you can just keep your answer in kilohertz as well. But I should have said my answer was in kilohertz. Okay, so I'm going to tell you a bit about the courses on Snap Revise. It's a lot of what we're doing here on YouTube and a load of other stuff as well. And it's 25% off this week. So now's the best time. And we'll look at some stationary wave stuff. So let's take a look at A-level physics, AQA. I'm going into my courses. And the Snap Revise course isn't just like a textbook or an online video course. It's a mix of the two. It's the best of both with a third quite important part. So the third important part is a kind of smart learning part. Essentially, the idea is there's a lot of quizzes here, and they're not just quizzes for you to tell how you're getting on. The key thing about these quizzes is they help to actually shape the course so that the course is more efficient and you only work on the stuff that's most important for you to be working on. So let's have a go at a quick quiz. And I guess I won't have time to do this properly, so I'll answer some random questions in the end. This will compile in a second. Here we go. So there's a few stationary wave questions here with answers along the way. Hopefully I'll get something right. Constructive interference. Which one of these is constructive? This one. Good. Okay. Which of the following pairs will produce a stationary wave? Maybe this? No, I didn't read it well enough. Okay. Okay, so I'm just answering random stuff so I can get you to what things look like at the end. 12, maybe it's a 3. Yeah. Just went for something that was a multiple of 12. That could have been any questions. Maximum energy, that would be the ones with the biggest displacement. Nice. Okay, so we're making progress here. Okay, that one was pure luck. And we'll do a few more. Wow, okay, I'm getting really lucky. I actually need to get less lucky. Whoa, okay. Sweet, okay, I got something wrong. I wouldn't do this well if I tried. Okay, right, okay, exactly 50%. That could have gone better. Yeah. I'm promoting what we're doing on the website, absolutely right. Okay, so here's what I did. Let me take a look at what's going on now. So I'm going to end up in our actual course, and it's a video course, first and foremost. But the key thing is that now I've done the quiz, it's set up and everything's highlighted to show me what I actually need to work on. So for example, the green stuff is not the stuff I need to look at, it's the orange stuff. And within each video, actually the bits of the video that I need to look at are highlighted as well. So let's take a look at this one here. And again, I need to know both of these bits. Okay, great. Now, once I've actually gone through the course, then I can look at some more quizzes and see how I've improved, etc. And I can look at some exam questions where we've actually gone through some exam questions ourselves, showing you how we would do them. So you can get a bit of our exam technique as well. So outside of that, there's all sorts of other things. There's revision cards that we've been making, and there's sessions like this. So all these live streams that we're doing here, which we're going to do occasionally. So we're gonna do things occasionally on YouTube, but also we're doing about 4 or 5 of these web classes a week on the Snap Revise website itself. So I'll briefly show you the schedule for that, and then I will make a move. So, I will make a move right now because there is a class starting right now, which I'm going to do on electric fields. But this one is on the Snap Revise website. Okay, thanks very much for coming, everyone. I hope it was useful. And the last thing I have for you is just to share with you the code so that you can have 25% off of this if you would like it. So let me find that now. There we go. So here's the code. Thanks very much for coming, everyone. And hopefully see you at another session, either here on YouTube or on the website soon. Okay, thanks very much. Bye.